think the recording is not started. Okay, fine. Okay. Decrease in available energy when heat is transferred or finite temperature difference. So here we have this Carnot cycle which operates between the source temperature T1 and your ambient temperature T0. Okay. And we have already seen you can define Q1 as T1 into delta S. We have seen this. So integral TdS that will give you your heat supply. Okay, so that is given as T1 into delta S. So this delta S, other way around when we did it in entropy, okay, when we did it in entropy, we said delta S as using mouse is very difficult than using my hand. So Q1 divided by T1. Okay, we said this is the heat supply from source divided by the source temperature. So that was your delta S1. We did that when we talked about entropy. Similarly, delta S on the sink
Sir,
side would be
sir, your voice is breaking, sir.
yeah, kindly adjust because I'm here in the auditorium. So is it okay now or is it still breaking?
Still breaking, sir.
How about now?
So
Is it
it's
still breaking?
slightly better.
Yeah. Okay. I'll try my level best. So if it is if it is very difficult, then you can let me know then. Okay. So we have computed the change in entropy by heat divided by the temperature. So this is the heat supply from the source divided by the temperature of the source. Okay. So similarly, Q2 written as T naught into delta S. We have seen that when we talk about entropy. So your W is useful work, which is Q1 minus Q2. And so because we have defined Q1 as T1 delta S and Q2 as T delta S, I write it as T1 minus T naught into delta S. Okay. And now what we are doing is we are talking about heat transfer through a finite temperature difference. Okay. So now what I do is, okay, I have an amount of heat in my hand, say Q1 amount of heat, say 500 kilojoules of heat is there in my hand. What I'm going to do is at a particular temperature T1, okay, say the temperature is 100 Kelvin, and then I have not 100 Kelvin, let's say 400 Kelvin, T1 is 400 Kelvin. Okay, what I do is T1 dash is at 350 Kelvin. So when there is a finite temperature difference, there is going to be heat transfer. Okay. So T1 is at 400, T1 dash is at 350. So there is a temperature difference of about 50 degrees centigrade, 50 Kelvin. Because this temperature difference, there is going to be a heat transfer. Okay. That heat transfer is going to be there and we call that as Q1. This heat transfer is not because of running an engine. This heat transfer is because of the temperature difference. Okay. Now what we are trying to do is we will try and see this is the amount of heat that's been transferred from T1 to T1 because of the temperature difference. So let me find out the change in entropy or the available energy, okay, running a heat engine between T1 dash and T naught. Okay. To understand two things here, there are two steps involved. The first step is there is a finite heat transfer because of a finite temperature difference between T and T1 dash. Okay. The second one is to estimate the available energy, we are going to run a reversible heat engine between T1 dash and T naught. Okay. That is what we're going to do. Okay. So initially when you have temperature at 400 Kelvin, say T1, okay, you have certain amount of energy. Okay, so that call it as T1 into delta S. Just like did here for the Carnot cycle and figure 8.4. Now what we do is we are coming to figure 8.5. Now what I'm saying is Q1 is the amount of heat supplied to the engine that runs between T1 dash and T naught. That is one point. The second point is Q1 is the amount of heat that has been transferred due to the temperature difference between T1 and T1 dash. Okay, both are equal amounts of heat. So that is something which you should understand. Q1 is the amount of heat that has been transferred because of the temperature difference between T1 and T1 dash. The same amount of heat has been absorbed by the heat engine, or that is taken by the heat engine to run the heat engine or to deliver the required work output. Okay, so that is your Q1. Q1 is T1 to delta S. Okay, that you are familiar. We have already seen. But this Q1 equal to T1 into delta S. This is the temperature T1, which we have assumed to be 400 Kelvin. So this is 400, just for an example. So this is 400 Kelvin. And for this, the delta is here. Okay, the delta S is here. Why we are doing this? So now we are trying to say if I am going to run a Carnot engine between T1 and T naught, this would be the cycle. Are you able to understand? So if I am going to run a Carnot engine between T1 and T naught, this would be the cycle. Between T1 and T naught, this would be the cycle. This would be the cycle if I run a heat engine between T1 and T naught. Okay, and that is the case, then Q1 is T1 times delta S. So delta S you can see here. So this is delta S. So this is your Q1. Okay. Now what I'm doing is, so that same amount of Q1 has been absorbed by the heat engine when it runs between T1 dash and T naught. So that is the second cycle that you can see here. Okay. So let me use another color here. Uh, Maybe this orange. Okay. So this is the next cycle when the heat engine runs between T1 dash and T naught. Okay, so for this, Q1 will be T1 dash and delta S dash. Is that clear? So this is your Q1. Your Q1 can be written as T1 into delta S when a heat engine runs between T1 and T naught, and Q1 equal to T1 dash into delta S dash when the heat engine runs between T1 dash and T naught. Okay, and what we are familiar that this T1 is greater than T1 dash. As T1 is greater than T dash, we said T1 dash is somewhere around 350 Kelvin. Just for an example, we have taken this value. So this is 350. Okay. So because T1 is greater than T1 dash, T1 is greater than T1 dash. Okay. So your delta S dash is greater than delta S. What is the definition of delta S? So delta S, if you say, if you take it the other way around, so delta S can be written as Q1 by T1. Okay. And what is delta S dash? So delta S dash is going to be Q1 divided by T1 dash. What you should remember is this Q1 is the same entity, 500 kilojoule. 500 divided by 400. Okay, for example, let's say 500 divided by 400. So 5 by 4. So is it 1.25? Okay. What about here? So this will be 500 divided by 350. What is the value of 500 divided by 350? Can anyone compute this and tell me? So this would be 10 divided by 7, right? So 10 divided by 7,
So 1.428, sir.
1428. So obviously now you can see that your delta S dash is greater than delta S. Just to give you that understanding, I have taken this numerical example. Okay. So when you divide the same entity with a greater number, you have a lesser value. and when you have the same entry divided by a small number, you have got a greater value. So your delta S dash is going to be greater than delta S. Okay, so this is for the heat supplied region. But if you look at the sink is going to be at T naught. Okay, so your Q2 is going to be T naught into delta S. That is for the first cycle. When you run the first cycle, you have Q2 equal to T naught into delta S. And for the second cycle, the orange cycle, your Q2 dash is T naught into delta S dash. Okay, and just like the previous case, since delta S dash is greater than delta S, your Q2 dash will be greater than Q2. What do you mean by this? Your Q2 dash is greater than Q2, so you are rejecting more amount of heat when you're running a heat engine at a lower temperature than when you're running a heating at a higher temperature. Heat rejection in the second cycle is more than the heat rejection in the first cycle. Okay. Okay. So your W dash is Q1 minus Q2 dash. So Q1 is the heat supplied. Q2 dash is the amount of heat rejected. Okay, and that heat rejection takes place. That heat rejection takes place in the second cycle. Okay. So Q1 minus Q2 dash. What is the W dash? W dash is the amount of work done in the second engine between T1 dash and T0. W is the amount of work done in the first engine, Q1 minus Q2. So that is T1 minus T0 into delta S, and this is T1 delta S dash minus T0 delta S dash. Okay. So obviously you can find that when you're running a heat engine at a higher temperature, you're going to have more work done. So your W dash is lesser than W because your Q2 dash is greater than Q2. This you know. So we know that we know that we know that W is Q1 minus Q2. Okay. So if you are going to have more work done, you are going to have lesser amount of heat rejection. Okay. So if your heat rejection is going to be more, obviously that is at the cost of the work done. Okay. So your Q2 dash is greater, which means your W dash is lesser. Okay. So that we already know. The common sense should tell us that. So W minus W dash will give you E naught into delta S dash minus delta S. What is this? This is the energy which is unavailable to us. Okay. When you are running a heat engine at a relatively lower temperature. If you would run the heat engine if you would have run the heat engine between T1 and T naught, the unavailable energy would be simply Q2, which is T naught into delta S. Are you able to understand? So if you are running the heat engine just between T1 and T naught, the unavailable energy will be T naught into delta S. But now you're running an engine after there is final temperature difference, which is T1 minus T1 dash. So that gap, there is a 50 degree centigrade or a 50 Kelvin lesser than source temperature. So because of that, you're running a heat engine after a temperature difference, and that has resulted in a higher change in entropy or a higher unavailable energy. So you can see this shaded region. Okay, so this shaded region is what we call the increase in the unavailable energy. Okay, so because initially you have got this delta S dash and delta S dash minus delta S, so this is an additional increase in change in entropy, and that is contributing to your increase in unavailable energy. So what we are saying is, so if the finite temperature difference is going to be higher, your unavailable energy is to be higher. Okay, so you should always run a heat engine with higher source temperature. Say it is better to run a heat engine at 1000 Kelvin source rather than running a heat engine at 100 Kelvin source. Okay, so 1000 Kelvin source will give you, so when you have higher amount of energy, more of the energy can be converted into work, useful work. When you have less amount of energy, only very, very small amount of lesser energy can be converted into work. Okay, so it is always better to run a heat engine at a very high temperature. Okay, so your the available energy which can be converted into work, it gets reduced as your temperature difference increases before running a heat engine. Is that clear? So if you are straight away running a heat engine between T1 and T0, your unavailable energy is only T0 into delta S. Okay, so that would be just this. So that would be just this region alone. Okay. Now when you are running a heat engine between T1 dash and T0, including this T0 into delta S, okay, you'll also have this region also. This entire region you will have. I'm not sure if you are able to understand this, so I'll use another color here. This entire space, this entire space is the unavailable energy when you are running a heat between T1 dash and T. Okay, and what is the increase in the unavailable energy? This is the additional part. You already had this region which I had hatched with the orange color line. Now I'm hatching with the green color line. So in the green color line, it comprises this region also. Okay, so this region is the increase in the unavailable energy. Okay, so it's always better to run a heat engine at a higher temperature. Okay, hope it is clear to you. Then the next one is available energy from finite energy source. Okay, so from a finite energy source. So now you have a TS diagram. So what you have here is, okay, this is like a heat exchanger. A heat exchange takes place here. You look at the process 1 2, process 1 3. If you look at process 1 3, you see that there is a gas. M dot G is a gas. It is moving in downward direction, or I would say it is actually moving from 1 to 3. It is losing heat. There is a drop in temperature. At 1, it is higher temperature. At 3, it is lower temperature. So there is a drop in temperature. Okay. And because there is a drop in temperature, it is a heat rejection process, which means your entropy is decreasing. Your entropy is supposed to be negative and it is heat rejection. So there is a negative entropy change and there is a fall in temperature. Okay. So there is a gas flowing at m dot g, the mass flow rate of the gas, and this gas is giving out Q1 amount of heat. Okay. And there is another fluid, say water, W, maybe water, just for an example. Water is a fluid, WF. It comes across this gas, and whatever heat is lost by this gas is gained by this water. Okay. So you can see Q1 is GCPG into T minus T naught. So the temperature difference. So heat is being lost by this gas between the temperature levels T and T naught. So it is mgCP into T minus T naught. mCP delta T. That is the same formula that we use here. So the same formula is used here. And the say whatever heat is ejected by this gas is gained by this water. And so we are writing this as MWCPW into T minus T naught. Okay. And you have the heat transfer, can the area under the curve will give you the heat transfer. So they have given you this 14531. So that is the amount of heat transfer during this particular process. Okay. And then to complete the cycle, they are showing that so 3-1 is the heat gained. Okay. And then the 1-2 is an expansion process at constant entropy. So this is an isentropic expansion. And 2 to 3, um, entropy is dropping again. So it's supposed to be a cooling process. And then you have 3-1, which is a heating process. Okay. And now your T minus T naught is same because whatever heat is lost by this gas, whatever heat is whatever heat is lost by this gas, that is gained by this water. Okay, so that is going to be your T naught. So the T minus T naught is same for both the cases, which means this MGPG usually have a name called capacitance rate. Okay, that you will be doing when you in heat transfer when you talk about heat exchanges. So this heat capacitance rate, which is the product of mass and the heat capacity, specific heat mg into cpg, that is equal to mwf into cpwf. Because the steam energy not the same, these two entities should also be the same. Okay. Then we find the change in entropy of the change in entropy of the gas. You know, the temperature is dropping, so you know it is integral ds. Integral um, dq by t. Integral dq by t. dq is mcp delta t. So that is dt mg cpg dt by t, and this can be taken as constant on the outside. Initial temperature is T, final temperature is T naught, because the process is from 1 to 3. That's a drop in temperature from T to T naught. Okay. So you have mg cpg into ln of T by T. And so far, with whatever we have studied, this value is supposed to be negative because there is a drop in temperature. This is heat rejection. Okay. And then you have delta S WF. So is it okay now? Are you guys able to listen to what I'm saying, or is the voice still breaking? Is it okay, guys? Or you can reply.
So it's breaking in middle, sir, sometimes.
Sometimes it is breaking, but are
Yes,
you able to follow?
yes, sir.
Okay. If it's very awkward, then you can let me know. Okay. So unless you give me the feedback, I will assume that everything is fine and I'll just continue. Okay. So if it is very much disturbing or you're not able to get anything, you can just let me know. Okay. So delta is WF. So that's the entropy change for the fluid which is acquiring the heat. So it is the same thing, but here I have made a mistake here. So this should be between the temperature limits T naught and the temperature limit T. So this should be between T naught to T. I have corrected it here. While copy pasting, I made a mistake here. So this is supposed to be T naught to T. So final temperature by initial temperature. So ln of T by T naught. And again, by common sense, we know this is supposed to be positive. Okay, this is positive because this is gaining heat. So this is supposed to be a positive entity. So if you are taking the universe, so the delta S of gas plus delta S of WF, find it to be zero because both these terms are one and the same. This term is negative, this term is positive, and we have already seen this MgCpg is going to be same as MWF So the same values that you are getting, only with the sign being altered. So when you add it up, you are going to get zero. So delta S of universe is going to be zero. Okay. So if you look at heat rejection, Q2, for our definition, so Q2 is T naught times delta S WF. Okay, so we are taking T naught into MWF PWF ln of T by T naught. So this is your Q2. So what is the available energy? Available energy is W max, which is equal to Q1 minus Q2. So Q1 is mg cpg T minus T naught, and Q2 is T naught mg cpg ln of T by T. That gives you the area 1231. Okay, so this region, this triangular region, so this triangular region, this area is the available energy. This area is the available energy. So what is the unavailable energy? Can anyone tell me? What is the unavailable energy? So which area will be the unavailable energy? Very simple. Which area is the available energy? The available energy is area 1231. So which is the unavailable energy? It's actually mentioned in the graph itself. If you look very carefully, you will be able to see where the unavailable energy is.
It's the rectangle below.
Yeah, rectangle 24532. Okay, they have already given this as UE. UE is unavailable energy. So this region this region is going to be the unavailable energy. Okay, so just like we saw in the previous case, this is nothing but T naught into delta S, right? This is T naught into delta S, T naught into S2 minus S3 or S4 minus S5. If you look at the previous case, here we said T1 minus T naught into delta S. Okay, sorry, this one. This one. The unavailable energy is T naught into S2 minus S. Okay, look at this graph. So this region below T naught, and this is your Y, this is your Sx portion. So this is your Sy, and this is your Sx. Okay, so T naught into Sy minus Sx gives you the unavailable energy. The same thing here. T naught into S4 minus S5 or T naught into S2 minus 3 gives you the unavailable energy. So you can understand that. So it can be a generic sense that your unavailable energy can be simply defined T naught into delta S. Okay, that you can keep in your mind. Then quality of energy. So quality of energy, you are taking another example here. So figure 8.7, if you look at it here, heat loss from a pipeline. Heat loss from hot gas flowing through a pipeline. Okay, so the entry is at here, A, and the exit is at B. So M is the mass of gas entering through this pipeline from this end, and it is moving towards the other end, PB. Okay, and as it goes, it is losing heat. So that is why we call it as a heat loss. So the gas or air that is entering at point A and leaving at point B, as it moves, it is losing heat step by step. For example, just for your understanding, for convenience sake, let me say it is entering at 100 degrees centigrade. So when it comes somewhere over here, it becomes ET. When it comes here, it becomes 6. Then when it comes here, it becomes 40. And then when it leaves at 30. So when you study heat transfer, they talk about temperature distribution. The temperature gets distributed like the temperature, there's a drop in temperature as you move in the negative direction of x. Okay, we usually represent x as positive x-axis, right? So now your temperature is dropping in the negative direction of that is as I move towards the left, my temperature is decreasing. Just for an example. So that is what is happening here. Okay, and we are interested in two locations. One location here between T1 dash and T1 double dash. Similarly, another location at T2 dash and T2 double dash. Okay. So now let's see what happens. So this loss of heat, the loss of heat is happening to the surroundings. So we are going to divide this into two cases. One is the loss of heat to the surroundings as the temperature drops from T1 dash to T1 double dash. Okay, that is the first thing that we are going to see. Simple heat transfer MCP delta T give you MCP into T1 dash minus T1 double dash. Okay, and just like the previous cases, so if you look at the diagram 8.8, figure 8.8, you can see there is a drop in temperature from T1 dash to T1 double dash. And for this element, which we are considering, the change in entropy is delta S1. Okay, so T1 into delta S1. So between T1 dash and T1 double dash, if you take the average, you get T1. So T1 into delta S1 will be the uh, heat that is lost to the surroundings. Okay, when the temperature falls from T1 dash to T1 double dash. Similarly, if we assume that Q is the amount of heat loss that takes place when the temperature falls from T1 dash to T1 double dash, I assume the same amount of heat loss happens when the temperature drops from T2 dash to T2 double dash. It need not be, but we assume that the same amount of heat loss happens when the temperature drops from T2 dash to T2 double dash. There is heat loss that happens between T1 dash and T1 double dash to the surroundings, and I assume The same amount of heat loss happens when the temperature drops from T2 dash to T2 double dash as well. T2 double dash is this point and T2 dash is this point. And the average T2 dash and T2 double dash is T2. Okay. So if that is the case, then the heat loss for this particular temperature difference is mCp into T2 dash minus T2 double dash. And by definition, we can also call it as T2 to delta S2. Okay. And so here W is Q minus T naught into delta S1. We are talking about useful work. Okay. So the heat loss is Q. Okay. And anything below T naught, we know that is unavailable to us. So that T naught into delta S1 is the amount of heat that is rejected to the sink. Okay, so that T naught into delta S1 is subtracted from Q. So this is loss, the total heat loss. So that total heat loss would include everything that is being hatched here. Okay, so everything that is hatched here, this entire region is MCP into T1 dash minus T1 double dash. Okay, sorry about that. This region, at the bottom, I think I'm not sure if it is visible. Okay, so this region is T naught into delta S. Okay, so I'm sitting at desktop here. I don't have very good colors to show the difference. So this region, okay, this is fine. So this small rectangle or quad shape, T naught to delta S1. Okay, that is the amount of heat rejection. Okay, of the total heat that is being lost. Some of them can be converted into work, and what is that can be converted into work is Q minus T naught into delta S1. So that W1. So similarly, you can also find W2, which is Q minus T naught to delta S2. Okay, and since T1 is greater than T2, okay, since T1 is greater than T2, you can see this is at a higher temperature. At a higher temperature, the amount of unavailable energy is only this small square. See, the temperature has dropped to T2, and look at this. You're getting a big square here or a big rectangle here. The area of this particular portion is greater than the area of this portion. Okay, so when you are running an engine at a higher temperature, it is advantageous. When you're running an engine at a temperature, you have got more heat rejection in terms of entropy change. So delta S1 is lesser than delta S2. Okay. And you can remember the previous example that I gave you. So if Q is the same amount of heat loss, I showed you with numerical value 500 kilojoule divided by 400, it gives you 1.25. 500 kilojoule divided by 350 gives you 1.42. Okay. So if you are having a lower temperature, your enthalpy change is going to be higher. Okay, and that contributes more to unavailable energy. So your W1 is greater than W2. Okay. So the available energy at higher temperature is more than at a lower temperature, and the available energy decreases, temperature decreases. That is what we saw in previous slide also. Okay, so it is always advantageous to run an engine at a higher temperature. Okay, so for example, say if you have a temperature source 1000 Kelvin. Okay, you have a temperature source at 1000 Kelvin, and the heat loss here, or heat which I have lost instead of it into a work or converting it into work, say that is 1 kilojoule. Okay, and say there is another heat engine which is just running at Kelvin. The source temperature is just 100 Kelvin, and here also the heat that is being lost is 1 kilojoule. Now, which do you think, where do we have more unavailable energy? we may think that this fellow is better, but in a real scenario, this fellow could have been utilized much more because at 1000 Kelvin, the temperature is huge, and the temperature difference with respect to the surroundings is also huge. So this joule could have been converted into work, whereas at 100 Kelvin or at maybe 300 Kelvin, but 300 Kelvin, temperature difference with respect to the surroundings is very less. Okay, so the amount of energy that is available itself is very less. So this 1 kilojoule, even if I am going to use or not use, that is not going to be beneficial to me. Whereas at 1000, the temperature difference is huge. I could have better utilized this 1 kilojoule. Okay, so that's something which you should keep in mind. Okay, so it's like the bank account example you can take. Say you've got 1,000 rupees in your bank account. The minimum balance that you have to maintain is 100. So if you don't use it, the amount that is available at your disposal is 900, and 900 can be utilized for purchasing something. Okay, something good. Okay, but in your bank account you have only 150 rupees. Okay? And the minimum balance is 100. So what is available at your disposal is just 50, and that which you can achieve with 900 is very much greater when you compare it to what you can achieve with 50 rupees, right? It is like uh, it's almost 20 times, right? Approximately 18 times greater than the 50 rupees that you have in your bank account. Okay, when you have 900, you can do 18 times more than what you can do with 50 rupees. Similar is the material here. So when your temperature, the source temperature is higher, you will be able to perform more work. Okay, so in that scenario, when you are losing something, then that is a very big loss because you could convert that to something else, which, which could be very much beneficial or could be very much useful. So when you have a high temperature source, you should concentrate much on insulating the high temperature source. Okay, so that is the quality of energy. The quality of energy is high when you have a high temperature source, and the quality of energy is low when you have a low temperature source. Okay, so that's with reference to the quality. The first law talks about the quantity. The first law talks about quantity of energy. It simply says all work can be converted into heat, and all of heat can be converted into work. Or I should not say converted. I should say sum of heat transfer equal to sum of work. So all of heat is equal to all of work. All of work is equal to all of heat. Okay, but what the second law tells us is it talks about the quality of energy. Because all of heat cannot be converted into work, it now you are able to qualify the energy. You can say this energy is superior, this energy is not superior. So if you have a high temperature source, that is a high quality source. If you have a low temperature source, it is actually a low quality energy. Okay, keep that in mind. So the second law, they also call it the law of degradation of energy. You take the first law, the law of conservation of energy. If you talk about the second law, it is the law of degradation of energy. So it is able to qualify your energy, whether it is a high quality energy or a low quality energy. Okay, so that is something which you can keep in mind. There is maximum work in a reversible process. So if you look at the slide, so I have one process, one two, which is a reversible. So this process takes a reversible path, and one two takes an irreversible. So and during this process, heat is being rejected to the surroundings. Uh, sorry, uh, heat is supplied into the system. So if you look at this particular diagram, heat enters into the system and work is done by the system. So both Q and W they are positive. So U is equal to delta U plus W, U2 minus U1 plus W, and this is for a reversible path. This is for irreversible path. And to find the difference, QR minus QI, because your heat and work they are path functions. So if you are going to have a different path, then there is going to be a variation in that amount of heat transfer and the amount of work transfer. So QR minus QI, this U2 minus U1 is going to be the same because this is du, and du is a point function, and you have the same points 1, 2, two different paths. So U2 plus U1 is going to be the same both reversible path and the irreversible path. So this U2 minus U is same. So if you just retain it on one side, QR minus W to QI minus WI, or the other way around, QR minus QI is equal to WR minus WI. So if I equate it, if I say U2 minus U1, this is equal to QR minus WR. Similarly, you can write U2 minus U1. This is equal to QI minus WI. So now you can equate these two equations. Because the left hand sides are equal, the right hand are going to be equal. So you can write QR minus WR equals minus WI. Now if you rearrange this equation, you will have QR minus QI equal to WR minus W. That is what we have here. Okay. So the delta S for the system, so delta S for the system, it is from change from the state 1. So S2 minus S1, the change in entropy of the system. What is the change in entropy of the surroundings? You are having Q amount of heat entering into the system from the surroundings. So the system is gaining heat. So the other way around, we can say surroundings is losing heat. The surrounding is at a particular pressure P naught and that pressure T naught. So because it is losing Q amount of heat, it is minus Q by T naught. It is losing heat, it is minus. Okay. So by the law, your delta S of the universe should be greater than or equal to 0. Okay. It cannot be less than 0. Less than 0, it is impossible. Greater than 0, it is an irreversible path. And for equal to 0, it is going to be a reversible process. Okay. So for a reversible process, delta S of the universe should be equal to 0. That is why they have put equal to 0. And they have said delta S of the universe is nothing but delta S of the system plus delta of the surroundings. So delta S of the system is S2 minus S1. Delta S of the surroundings is minus Q by T naught. And because they say reversible, they have given QR, R for reversible. So this is the heat transfer reversible path. Okay. So QR. So if I just consider this equation, S2 S1 minus T naught equal to 0, QR is equal to T naught into S2 minus S1. Okay. So that is the heat transfer in case of a reversible process. So for an irreversible process, instead of equal to 0, you should have greater than 0. Sorry. So your QI is less than T naught into S2 minus S1. Okay. So your QR is greater than QI. Your heat transfer reversible path is greater than heat transfer in the irreversible path, which means heat addition in case of the reversible path is greater than heat addition in case of the irreversible path. And that is, you can infer that from the graph. What is the area under the curve of the reversible path? This entire region, right? This entire region is area under the curve for the reversible path. And what is the area under the curve for the irreversible path? It is just below the dotted line, and there is only this region, the blue hatched line. Only this region is the area under the reversible path. Okay, so obviously your QR is going to be greater than QI. That means your WR is also greater than WI. If you draw that in the PV diagram, that will be very obvious. And we have already done, now we are just doing it in terms of the available energy. We already know from the Carnot's theorem that your Carnot engine is the only engine that is having the reversible processes. So your Carnot engine is going to deliver the maximum. So from the viewpoint of entropy and available energy, now we are able to see that the reversible process you are going to have maximum work. Okay, I don't think there is much of a complication here. This is an already known thing, but from a different viewpoint. Okay, the other one is the work done in all reversible processes is the same. Okay, so you have this also we have done. This is another way of the Carnot's theorem. The Carnot's theorem says if you're going to have any number of engines running between the same temperature limits, running on the reversible processes, then you're going to have the same work done or the same efficiency. Okay, so this we have already done. So this is a very well-known concept. Work done in reversible processes is going to be the same. Okay, and this is important. Reversible works by open system, exchanging heat only with the surroundings. Okay. Just observe figure 8.1 carefully. Okay, if you look at this figure 8.1, you can see that this is the device. Okay, this is the control volume, and in this control volume, you can see that uh, you can see dm1 is the amount of fluid that is entering into this device. dm2 is the amount of fluid that is leaving this device. So looking at this, you will be able to understand that this is a steady flow energy device. Okay, and this is an open system. Okay, and this we have already done. H1 is the enthalpy at the entry. V1 squared by 2 is the specific kinetic energy at the entry. G1 is the specific potential energy at the entry. The same holds good here also. So this is the enthalpy, specific kinetic energy, and specific potential energy at the exit. Okay, and you are receiving dq amount of heat into the uh, device, and the device is performing dw amount of work. Is giving out a dw amount of work. Okay, and this dq is nothing but the heat rejection by an engine that runs between T0 and T. So this device is at temperature T, and the surrounding is at temperature T0. Okay, and if you are saying that this is at a temperature T, so this surrounding or this is at a higher temperature. Maybe instead of saying it as a surrounding, maybe this is the boiler. This boiler is rejecting heat to this device, which is at a temperature T. Okay, this is at a temperature T. Okay, so this is a reversible engine, and it is delivering some amount of work, and that is given as dWc. And both of them can be added up together, and this gives you the dW max, which is dW plus dWc. Okay, and this is d of u plus mv squared by 2 plus mg is it. So this is the change. So if you look at here, dm1 is the mass that is entering in, dm2 is the mass that is leaving out. So what they are saying is, when you say m is taken inside, which means the some amount of mass is being stored inside the device. So it is not a steady flow system. There is a change in mass. If there is no change in mass, it becomes a steady. When the properties do not change with respect to time, well, it is steady. If the properties change with respect to, then it is not steady. Okay, so you have got m. There is a variation in some amount of, not all of the mass that is entering in is leaving out. Some amount is retained inside. Okay, so that change in energy, d of u plus mv squared by 2 plus mg is it. That is the change in the energy of the system. In a closed system, we simply call it as change in internal energy. Now we simply call it as change in energy. Now if we write a simple energy balance, Q is equal to delta U plus W. Okay, Q is equal to delta U plus W. Okay, so if you look at it, dq. So we know from the first law that dq is equal to, now because all other terms are also there, so we have to use E. So apart from the internal energy, there is also kinetic energy and potential energy. Okay, and now they are doing is they are simply uh, retaining the change in energy on one side and dq minus dw is equal to this dE, and this dE includes the energy at the inlet. We have seen this before. Energy in minus energy out is equal to energy stored. We have done this before, if you remember. Okay, so that's the C. So now what is being retained is the energy stored alone is said or retained on the left right hand side, and this energy in minus energy out is taken to the left hand side as well. So you can see dq is the amount of heat that is entering. This is the energy that's entering into the device. This is the energy that is leaving the device, and the dw which is on the right hand side is taken to the left side. So this is minus dw. Okay, and you can see, don't see this is work input. This is not actually work input. Work is actually out. Work is done by the system. Because we are pulling it to the left hand side, you have got a minus. So be careful about this minus sign. This minus sign doesn't mean it is work input. We have pulled it to the left hand side, so you have a minus. It is still work output. Okay, that is equal to dE, and E. Uh, so this sigma represents the control surface. So they have given you a sigma here that represents, that is the change in energy inside the control surface. Okay, dfu plus mg squared by 2 plus mgz. So this is a simple energy balance equation. Okay, and we know from this is a reversible engine, this is a reversible heat engine. So according to absolute thermodynamic temperature scale, we know that dq naught by t naught is equal to dq by t, and that is applicable only for a reversible engine. You can see the reversible sign here. Okay, E followed by a circle with two arrow marks. So this shows that it is a reversible engine. Okay, so you because it is reversible, we can write it dq naught by t naught equal to dq by t. Okay, and what is this dwc? Then is nothing but heat supplied minus heat rejected. So dwc is dq naught. Dq naught is the heat supplied minus heat rejected is dq. Dq naught minus dq. And so I can write this as, from the previous equation, dq naught can be written as dq by t into t naught. I can take this t naught and put it over here. And I have replaced my dq naught with dq into t naught by t. And so your dq is dq into t naught by t minus 1, dw. The total work then is the work that is delivered by the device plus work that is delivered by the engine. You can see here dw max is dw plus dwc, figure 8.11. Okay. Now we have the entropy change. Again, we have done this when we talked about entropy. The change in entropy is because of the entropy change due to heat transfer and the entropy change due to the mass transfer. Okay, so term this term dq is because of the heat transfer, and this term is because of the mass transfer. Okay, so your dq by t can be written as ds, the total entropy change, is because of the contribution of the heat transfer and the contribution of the mass transfer. So dq by t can be written as ds minus dm1 s1 dm2 s2. Okay. And if we come to this part of the slide, so dw max is the dw of the reversible process, and in this particular case, it comprises both the work delivered by the device and the delivered by the engine, dw plus dwc. So dw, we don't have a specific term, so we retain it as such, and dwc, we written this as dq to t naught by t minus 1. Okay, if I hope this is clear to you, at least the steps which I have explained. Okay, so if you have doubts, you can stop me and ask me. Okay, so this is your dw max. And now, if you look at it, if you look at, sorry, If you look at this particular first equation, you have dw, right? So now what I want is dw max. So if I want to find dw max, I can take dw to the right hand side and pull everything else on one side. Okay. So you have dw max is dq plus the energy at the inlet minus energy at the exit. And this was energy stored, which was on the right hand side. Now I pulled it to the left hand side. Okay. Okay. If you look at this, so this term, no change. This term is brought to the left hand side, and this dw is taken to the right hand side. And what is that dw? That dw is dwx minus dwc. Okay, dw is dw max minus dwc, and dw max is written here. So minus dwc has to be there, and that dwc is taken to the right hand side, and that dwc is dq into t naught by t minus 1. Can you see this? dwc is dq into t naught minus t minus 1. Here you have dw, so your dw is supposed to be d max, sorry, dw max minus dwc. Okay, and here you have dw. So when you take the dw to the right hand, you have dw max minus dwc. Now you are having dw max alone on one side. So this dwc should be on the other hand, and the value of dwc is dq into t naught by t minus 1, and that is what you see in this plus slide. Okay, and now here you have dq, and here it is dq into t naught by t. If you open the brackets, it becomes dq into t naught by t minus dq. So this dq and this dq will get cancelled, and you will simply have dq into t naught by t. Okay. This dq by t is nothing but the change in entropy. So we have already defined change in entropy, cyclic integral of dq by t. So here you have dq by t. So this is nothing but delta s. So if you look at the previous slide, dq by t is ds minus dm1 s1 plus dm2 s2. So that is being substituted here. So dq by t is ds minus dm1 s1 plus dm2 s2. That is being substituted here. Okay, and that is multiplied by t naught, which is already there. Okay, so because this you have ds, this ds can be written as s2 minus s1. This ds can be written as s2 minus s1. Okay, so that is t naught into s2 minus t naught into s1. So you can see minus t naught into s1 is absorbed into this first thing. Okay, and minus t naught into s2 is absorbed into the second equation. Sorry about that. Uh, the ds maintained as such. T naught ds is there. dm1 s1. So because you have d1 as dm1 as common, so when this here you have dm1, and because of that t naught into s1 is absorbed here, and t naught into s2 is absorbed here, and what is left out is t naught into ds. And this, so what is left out is plus t naught into ds. Okay, and you already have a d of, that means change of u plus mv squared by 2 plus mgz. This t naught is constant. Okay, and so there's no harm in writing this t naught as T naught ds as d of T naught s, because T naught is constant. So if you differentiate it, what you will get is T naught into ds. So there is no harm in writing it as T in d of T naught s, and therefore this T naught s is taken into this uh, d of term. Okay, so this you get as dw max. So this is the maximum work that is obtained when an open system exchanges heat with the surroundings. Okay, so this is all these equations. So for time, I have taken it directly from paper. So if you have doubt, ask me then. Okay, and similarly, reversible in a steady flow process. In the previous case, it was not steady. Some of energy was stored. Okay, now I am saying it's a steady flow process, which means there is no change. Whatever mass that has entered into the device, that is going to leave the device. So dm1 is equal to dm2 is equal to dm. Okay, so df u minus t mass. If you look at this previous equation, this last term, d of u minus e naught s mv squared by 2 plus mg z. This term becomes zero. There is no energy stored in the device. So there is energy stored. Whatever mass is entering the system, that is going to leave the system. Okay. So if that is the case, your d max is simply these two terms, dm1 into h1 minus t naught s1 v1 squared by 2 plus gz1 minus dm2 into h2 minus t naught s2 plus v2 squared by 2 plus gz2. Those are the only two terms that you have. The third term, because there is no energy storage, this particular term becomes zero. Okay, so we just have that. So the total mass flow, the integral form becomes, so if you integrate it on both sides, so you have dw max becomes w max, dm that is being absorbed in, so it is multiplied inside. Small h becomes capital H, small s becomes capital S. So this is mv1 square 2, which means kinetic energy, mg is the one which is potential energy. Okay, so that equation gets transformed into this. Okay, and this h minus t naught s is called as Keenan's function. Okay, and replacing, just like you say u plus pv is h minus t naught is Keenan function b. So you have b1 plus mv1 squared by 2 plus mg z equal to b plus mv squared by 2 plus gz2. This term, the b plus mv squared by 2 plus mg z, that is called as psi. So that's meant here. B plus mv squared by 2 plus mg z is called as psi. So you have psi 1 minus psi 2. In other words, this is the availability function at the entry, and this is the availability function at the exit. So W max is B1 minus B2. Okay. So if the kinetic energy terms and the potential energy are neglected, so if these two terms are neglected, you'll have is simply H1 minus S1 minus H2 minus T naught S2. So H1 minus H2 minus T naught S2 S1 minus S2. So on a per mass basis, so it is specific enthalpy difference minus T naught is specific entropy difference. So the whatever we have done in this case, now we are neglecting the energy stored here, and we convert H minus T naught as Keenan's function b, b plus mv squared by 2 plus mg, that is called as, which is the availability function. Okay, so this is the kind of problem that you will get. They ask you to compute the change in availability between two. You have to find psi 1, you have to find psi 2, and then you have to find out the difference psi 1 minus psi 2, and you have to get the final answer. So such kind of problems is what you will be getting. Okay, so this is the reversible flow process. And what about a closed system? So for a closed system, there is no mass change at all. There is no mass transfer. So d1 equal to dm is equal to 0. So if you look at the previous case, so what is, so in case of a steady flow device, we said this energy stored is 0. In case of a closed system, there is no mass transfer. So before two turns burnished, whereas the last term remains. Okay, so that is what you have here. So dw max is minus d of u minus t naught s plus mv squared by 2 plus gz. Okay, and this u, I should write like this: u plus mv squared by 2 plus mgz. All these together, put together, you can write it as E. Internal energy plus kinetic energy, potential energy is energy, E minus T naught S. So that is written here. That is what is written here. E is equal to U plus mv squared by 2 plus gz. So that makes E minus T naught S. So W max is simply E1 minus T naught S1 minus E2 minus T naught S2. If you look at the previous case, it was H1 minus T naught S1 minus H2 minus T naught S2. It was H1 minus H2 minus T naught into S1 minus. In this case, it is E1 minus E2 minus T naught into S1 minus 2. Okay, very simple, right? So your W max simply, so if the kinetic and the potential energy changes are neglected, it is simply U1 minus U2 minus T naught into S1 minus S2. In the previous case, it was H1 minus H2 minus T naught into S1 minus S2. So if it is an open system, it is in terms of enthalpy. If it is a closed system, it's in terms of internal energy. Okay. So that is what I have for today. So if you guys have any doubt, you can ask me.
So actually, we must go through all these derivations or only for the problem-based sums, sir?
Um, till now, no derivations have been asked so far in available energy. Okay, and this is the first time we are having available energy as a separate unit. So I'm not sure whether you will get derivation part, but I don't think derivation part is complicated. See, you have only one basic equation, right? This is the basic equation. This is the basic equation. So if you have understood what I said, then it would be very simple. There is nothing complicated here. It is similar to your steady flow energy equation. You can neglect these things: maximum work, quality of energy, available energy, finite energy source. All these are concepts. But when you come here, okay, reversible work by an open system, reversible work in a steady flow process, reversible work in a closed system. These things, these last four slides, I think that you have to you can keep in mind. That's very important. Okay. So what we do is, yes, someone wants to ask something. Please go ahead.
No, sir. Okay, it was.
Okay, fine, fine. Okay. So I'll stop the recording here.